A playground merry-go-round has a mass of 120 kg and radius of 1.80 meter, and it's rotating with an angular velocity of 0.500 revolution per second. What is its angular velocity after a 22.0 kg child gets onto it by grabbing its outer edge? The child is initially at rest. So what values are given here? We are given the mass of the merry-go-round. Let's represent it by m sub m, 120 kilograms. Radius is equal to 1.80 meters. And it's rotating with angular velocity of, so merry-go-round's angular velocity initially is 0.500 revolution per second. And we need this in radian per second, therefore we have to divide by 1 revolution and multiply by 1 revolution equivalent radians, which is 2 pi radians. Revolution cancels out with revolution, so we are left with 0.5 times 2 pi radian per second. That is equal to 3.14 radian per second. And the mass of the child, let's represent it by m sub c, is 22 kilograms. And the angular velocity or velocity in general for the child is omega sub m naught is 0 at rest. What we are asked is to find omega f once the child gets onto the merry-go-round. Alright, before dealing with the conservation of angular momentum, let's find out what the the moment of inertia of both the merry-go-round and the child. The merry-go-round is like a cylinder or a disc, so it has moment of inertia of 1 over 2 times its mass multiplied by the radius squared. That's 1 over 2. Mass is 120 kilograms. And the radius is 1.80 meter. And that's squared. That yields 194.4 kilogram meter squared. And the moment of inertia of the child is mass of the child r squared, because the child is now like a point mass. If this is a merry-go-round, the moment of inertia of the merry-go-round when the axis of rotation is the center is given by half mr squared. But the child is sitting right here. So the distance from the axis of rotation is r. Now the axis of rotation is away from the point mass, therefore we use mr squared. And the child's mass is 22.0 kilograms multiplied by the radius, which is 1.80 meters squared. That's equal to 71.28 kilogram meter squared. So now I have the initial velocities and the moment of inertia of the merry-go-round and the child. Therefore, now we can use conservation of angular momentum. Initial angular momentum must be equal to final angular momentum. The initial angular momentum is equal to mass of the merry-go-round. moment of inertia of the merry-go-round multiplied by its corresponding velocity, angular velocity, which is omega of the merry-go-round initial plus moment of inertia of the child multiplied by omega of the child initial, which is 0. And then we have the two coupled together, meaning they're moving together, therefore moment of inertia of the merry-go-round plus moment of inertia of the child multiplied by their common velocity, angular velocity. This is 0. Therefore, omega sub f will be equal to moment of inertia of the merry-go-round multiplied by its initial angular velocity divided by the sum of the moment of inertia of both the merry-go-round and the child. Plug in the numbers. 194.4 kilogram meter squared multiplied by the velocity, which was converted to radian per second, and that's equal to 3.14 radian per second, divided that by the sum of the moment of inertias, 24.4 kilogram meter squared, plus the moment of inertia of the child, which was calculated to be 71.28 kilogram meter squared. So the angular velocity after the child gets on the merry-go-round equals to 2.3 radian per second.